My brain hurts. I'm just not understanding Newton's third law.
Right? It makes no sense.
I really need to go back and review the material slowly to see if I can make sense of it.
Me too. Do you want to work together?
Oh, definitely. Let's talk about the classic example of a car crash. Like, I know if there's a crash between a large truck and a small car, I'd obviously rather be in the truck.
Yeah, that goes with what I know from real life, but we're supposed to believe that the force on the truck is equal to the force on the car.
Well, okay, let's assume for a moment that the two forces are equal and we can work from there.
Do you think we can use F equals ma to look at this?
I think we can always use Newton's second law. I think it's just one of those things that keeps coming up in physics.
So, since the mass of the truck is much larger, then its acceleration must be much smaller.
What?
Look, here's the same force acting on both. The truck has a large mass, big M, and the car has a small mass, little m. So for m times a to be the same, the acceleration of the truck must be much smaller than the acceleration of the car.
I still don't see it. Well, let me try throwing some numbers around. Okay, so if the force is 1,000 and the mass of the truck is 100, then the acceleration of the truck must be 10. And if the mass of the car is like 10, then the acceleration must be 100. Okay, alright, I get it.
Right. The acceleration of the truck is much smaller. That's probably why it's safer to be in the truck.
Because the larger acceleration is more noticeable?
That makes sense. If the car stops suddenly, it hurts because our body wants to keep going.
Because of inertia, yeah?
I think so. Isn't that Newton's first law?
Yeah. So what we feel is the acceleration, not the force.
That would make sense. Here, let's try a simpler example like a book just sitting on a table. The free body diagram of the book would look like this. The weight points down. The normal force points up. They're equal and opposite, which means they make an action-reaction pair.
They are equal and opposite, but let's check that we have a pair like the F by A on B and F by B on A. The weight is the force by the earth on the book. The normal force, though, is the force by the table on the book.
So I guess they're not a third law pair. From what you're saying, the pair would be the force by the earth on the book with the force by the book on the earth.
Alright, but then where do you draw the force by the book?
Well, the book is actually exerting a gravitational force back on the earth. But because the earth has so much mass, it's a really, really small acceleration.
Oh, okay. So then we would find the force by the book on a free body diagram of the earth.
Exactly. So we have a different pair here. F by table on book and F by book on table. We should draw F by book on table on the free body diagram of the table. I remember reading that you never find a third law pair on the free body diagram of one object because one force is F by A on B and the other is F by B on A.
Oh yeah, when I press on a wall, I do feel it pushing back a little, but if I were to hit it hard, the impact would hurt my hand. A heavier book will push more on the table, and the table will push back more.
Yeah, there must be two objects interacting. The two forces come together as a pair.
I think that's why the teacher said that action and reaction is a bad name. The two forces happen at the same time. You can't have one without the other.
I still have questions though. Like, what if the table breaks? Also, do the objects need to be touching? And how do I know which forces to put in the free body diagram?
One question at a time. The objects don't need to be touching, but in most cases they will. In the case of gravity, the two don't need to touch.
Right. Like the sun is pulling on the earth and the earth is pulling on the sun, but they're not touching.
Exactly.
So if the objects don't need to be touching, how do I know when I'm done adding forces in the free body diagram?
Well, first you check everything that's touching the object, and then you just add gravity. Like, only a few other forces can act at a distance. Magnets, that kind of stuff. Now back to the table breaking.
Are the forces still equal and opposite?
Well, if the table is still touching the book, then it must still be pushing on the book. But is the force just as big?
If both are falling down, the book is not pushing as hard on the table.
How do you know?
I think the push isn't as strong because the table is kind of moving out of the way. Think about it if they were both in free fall. The table wouldn't be doing anything to stop the book.
So the book wouldn't be pushing on the table either. And as soon as the table breaks, the book isn't pushing as hard on the table.
And the table's pushback will also be weaker.
So the two forces are always equal and opposite, even when the objects are moving.
Okay, I think I'm starting to get it. For every force, there's an equal and opposite force, and together they make a third law pair.
And those two forces are never found on the same free body diagram. So the normal force and the force due to gravity are not a third law pair.
Right. Thanks for reviewing this stuff with me. We make a good pair.
That felt a bit forced.